Right, hi everyone. So this is your video solutions to the questions you did for the mechanics section. First one is we've got constant acceleration, so this is going to be SUVAT. Determine the speed. Well, the speed is the magnitude of the velocity, so I'm going to need to find the velocity first because I'm given the positions I'm given the acceleration and velocity in 2 dimensions. So, first of all, set up my SUVAT, and I'm told that the acceleration is -4,2, and at time equals 0, so that is the initial velocity, I've got 7,6. I want to find the speed, so I'm going to use this first to find the velocity. So V is going to be equal to 7,6 plus 3 lots of the acceleration. So the velocity will be -5,12 meters per second. And then I'm going to find the speed by finding the magnitude of that. So, a bit of Pythagoras working, and nice easy one because it is a Pythagorean triple. So final solution there. Next bit, determine the change in displacement. Okay, so that means that I need to know how far it's moved from its initial point between t equals 0 and 3. So I think I've got enough information here to go on and use the easiest displacement formula, because I know that at time equals 0 its initial velocity is this. We've just found that its final velocity is this. And the acceleration, as we're told in the question, is constant, so we can use that. Okay, so you've got a choice. You could use either of these equations, because we know that the time's 3 as well, from 0 to 3 seconds, or you could have used this equation as well. I'm going to use the top one, so we'll get a half of 7,6 plus -5/12 times by 3. That gives me a displacement of 327 meters. If you write any of the solutions in I and J form, that's full marks as well. Right, next question. So this time, there is no mention that this is constant acceleration, and also the velocity here is a function of time. It's a quadratic. So even before the question starts, if we've got a quadratic equation, that means that the gradient is changing along this curve. Okay, so it can't be constant acceleration. It means that we're going to have this idea that we can differentiate displacement to find velocity, differentiate velocities to find acceleration, and integrate to work the other way. Right, let's get started. So state the value of c. Well, we're given this piece of information above, and when we substitute 0 in, we get the value of c to be 8. So that's a nice mark. We're then given 2 pieces of information. We're told about the deceleration. So if I find the acceleration, that is equal to the derivative of the velocity, which will give me 2 lots of at plus b. The other piece of information measures the velocity, so I can just use this. Substituting those pieces of information in, got to be careful, it's deceleration. So I've got negative 0.12. That happens at time being 5. So I've got 10 lots of A plus B. Okay, so that's my first equation that I can form. Next one, just going to keep that equation there, is the velocity is 2.96 at time being 18. So t squared, so 18 squared is 324. And then we've got t lots of b, so 18b plus 8. Subtracting the 8 here from that side, and then using your calculator to solve them simultaneously, we will get a equals negative 1/50th, or the equivalent decimal, and b to be equal to 2/25. Part C. Find to the nearest metre the distance between points P and R. So we know that the area underneath a velocity time graph, so if I integrate v with respect to t, this will give me the displacement, or in this case the distance. Let's do it. So we want between P and R. P is at time equals 0. R is at time equals 18. So that's what we're going to integrate between. And we've found our coefficients for our quadratic. So this is the integral that we're going to complete. Negative 1/50th of t squared plus 2/25 of t plus 8, and we're going to integrate that with respect to t. When we do that, we get minus 1/150 t cubed plus 1/25 t squared plus 8t, and we're going to evaluate that between 18 and 0. When you do that, you get 118.08, but the question says to the nearest metre. So that's my final solution. Okay, moving on. So this does lead you through quite nicely, this question. It tells you the order that's the best way of doing it to find the unknowns. So the first thing is it tells you to take moments about A. Before we do that, let's get the forces drawn on. So this here is my weight of the rod. I've also got the weight of that lamp at the end. 1.5G. And I'm going to have a tension in the chain. Just going to move that so it looks a bit nicer. Hold on. And we don't need it yet, but we will have, if it's hinged, we're going to have a vertical and horizontal contact forces. Okay, we don't know how that works. We've talked about this in a previous lesson with the hinges. Right, it tells us to do moments at A. So that means I need to find all the perpendicular components of this. So I'm going, if I've labelled that T, I need this angle here. So that's my perpendicular component and my parallel component, and I need to try and find that angle. Let's have a think. So if that's 120, the triangle ADC is isosceles, so that means that both of those have to be 30. which means that is 60 degrees because it's perpendicular to that point. Okay, so I've got t of cosine 60. I've then got to do the same thing for these components of the weight. I need the perpendicular one. And let's do a little bit of work just to work that out. This is a right angle triangle here. So that would have to be 30. This would then have to be 60, so this will be 30, and the same will be true for this one here as they're parallel. Maybe just to make it easier to see, if I grab these things, I'm just going to move the picture as well, but if you imagine this point just moving over slightly, we'd have these lines here being parallel together. It's maybe easier to visualise. Let's resolve it. So that's our cosine 30, and then we've got 0.5g cosine 30. Let's do our moments. This one's going anti-clockwise, so 0.4 times by t cosine 60. That's got to be balanced with the other two that are going clockwise. So 0.4 times by 0.25 g cosine 30. Let's just move that along a bit. Plus the whole length of the beam, 0.5 cosine 30. Okay. It's a fairly easy rearrangement because there's only one unknown there. So we're going to have all of this, so if I copy that, and I can divide by 0.4 cosine 60. And that's going to give me my value of t. So put that in the calculator, and we get a value of 21.2 newtons. Right, next bit is we want to determine the magnitude of the force exerted at A and the direction. So we set this up earlier. We had a horizontal component and a vertical one. With a hinge, we've basically just got to make a guess. It's very difficult to predict how those forces are going to be allocated, like the amount that's going to be allocated to the horizontal and how much will be allocated to the vertical. So we've just got to make a guess. The tricky bit with this question is we've got to re-resolve the tension, because we now want to form equations with vertical and horizontal forces, and this angle here is going to be 30 degrees. You can see that from knowing this triangle, that has to be 30. We worked out that this was 30 from the isosceles triangle, and these two lines here make a right angle. So 30, 30, that must be 30 as well. So we get t cosine 30, t sine 30. They're the only two that I need to do differently, because the weight is acting perfectly down or vertical, and then I've drawn in my x and y horizontally and vertically. So let's do the horizontal equation. So x has got to be balanced with t sine 30. Well, that's going to be really nice, because we've actually just found that, so we can just halve it. That's cool. And then the vertical one, we've got a little bit more work to do. I'm going to call up positive. So I've got y plus t cosine 30 is equal to both of the weights, which is 0.75g. Okay. X is going to be half of 21.2. And when we do that calculation, we get this. Substituting, not even needing to substitute it in actually, because we haven't got x in the other one. Obviously it's the vertical, isn't it? Silly. Y is going to be equal to 0.75 lots of g minus 21.2 cosine 30. And when we do that, I get negative 11.009 or whatever. Now, what that means in context is I've actually guessed the wrong way. That means that my force diagram, me guessing that the hinge had a vertical component going upwards, was wrong. It's actually down. It doesn't make a difference for the magnitude, because we're still going to square these and find that resultant, but it will make a difference to the direction, because the direction is going to be below the horizontal, not above it. So the magnitude, magnitude, is equal to that one squared plus, didn't really need the minus there, I guess. And when we do that, to 3 sig fig you get 15.3. And then to find that angle that is below the horizontal, so below horizontal, we're going to get inverse tan, because it's the opposite over adjacent, of 11.009 over 10.6, which to 3 significant figures is 46.1 degrees. Almost there. Last bit, so C suggests one improvement that could be made to make the model more realistic. So I think anything to do, I'd be very surprised if it didn't say that the chain was light, or if we had something that was inextensible, so we want to sort of poke holes at that. So I think, where have we got the information about the chain? Oh, I just had the diagram, that's annoying. Let's just read it. The chain is modelled as light and inextensible, so we could say that the model would be more realistic if we considered the weight of the chain. Okay. I think that's the easiest one to get them on. Right, I hope that's helpful, and I'll see you next week.